Hello everyone and welcome. I'm going to be going over the exam 2 for 2019 Spesh. I haven't really seen anyone make a YouTube video on this, so I thought I would. Honestly, this exam is cooked. I don't know what VCAA was thinking, but they were just like, fuck it, and they include every separator question possible. There was a lot of low percent questions in this exam, but overall, yeah, it was hard. I mean, who am I kidding? Well, let's just have a crack at it. Hopefully you guys don't have an exam as hard as this on Monday. Okay. Starting off with question 1, we have our parametric equations here, and it says show that you can write it as in the Cartesian form like that. So the main thing to notice here is that we have a sec t and a tan t, and we can relate these together by going onto our formula sheet and looking at this relationship. 1 plus tan squared t is equal to sec squared t. So let's go back here. 1 plus tan squared t is equal to sec squared t. So all we've got to do here is just solve for sec squared t and tan squared t, and we'll be able to get our Cartesian equation. So let's solve for sec squared t first. So we're going to be using this, subtract 1 to the other side, and then square both sides. Squaring both sides, I'm going to expand the left-hand side. That gives me x squared take 2x plus 1. And that's going to be equal to sec squared t. Okay? Now, similar approach for this gives us y squared is equal to tan squared t. Beautiful. Now, we can use this equation to figure out our Cartesian equation. So we go 1 plus, use a different color, 1 plus tan squared t, which we just figured out to be y squared, is equal to sec squared t, which we just figured out to be x squared take 2x plus 1. Now, subtracting 1 to the other side gives us y squared is equal to x squared take 2x. And square rooting both sides gives us y is equal to plus or minus root x squared take 2x. Now, the main issue here is we have a plus or minus. Now, how do we know which one to use? We need to figure out the range of y, okay? And the way we do that is by looking at the restriction on t. So if t starts off at 0, subbing that into here, right, because this is what our y depends on, gives us tan of 0, which is just 0. We can't sub pi on 2 directly in there, but as t approaches pi on 2, tan approaches, or tan of pi on 2 is, or approaches infinity. So that is our range for y. And since that has no negative values in it, we don't use a negative version and we just use the positive version. So that's our Cartesian equation. Now it says state the domain and range of the relation. We did just find the range, so we can go the range is 0 to infinity, and our domain we can figure out in a similar way by just considering this. So we know that sec t is just 1 on cos t plus 1. Now when we sub in 0 into this, that gives us 1 plus 1, which is just 2. So our domain starts off at 2. When we sub pi on 2 in there, we get 1 on 0. We can't have that, so we need to consider what happens to cos of t as t approaches pi on 2. As t approaches pi on 2, cos of t becomes really small. 1 divided by a really small number becomes really big. So that means this approaches infinity. So that's our domain. Okay. Now here it says find dy dx. That is just dy on dt times dt on dx. Okay. And we can figure these out quite easily by just going up and looking at our parametric equations. So coming up here, using this, we can figure out dy on dt as sec squared of t. And using this, we can figure out dx on dt, which is, I'm too lazy to figure that out, so I'm going to go on the cas. That gives me sine t on cos t squared. sine t on cos t squared. Perfect. Okay, let's copy these. Bring it down here. Now, we have dy on dt, right? That's good. But we need dt on dx. We don't have dt on dx, so we need to flip our dx on dt. So that gives us cos squared t on sine squared t. Okay, now just using these to work out dx on dy on dx, we get sec squared t, which is 1 on cos squared t, times cos squared t on sine t. Now these cancel, and we're left with a nice 1 on sine t. Okay? Now to state the limiting value of dy and dx as t approaches pi on 2. This is nice and easy, just sub pi on 2 in there and you get 1. Okay? Perfect. Now it says sketch the curve on the axis below for that domain. Now I want to work out the endpoints first. So I'm going to go when x equals 2, y is equal to root, subbing it into here, we get 4 take 4, which is just 0. So one of our endpoints is 2, 0. Okay? Now for the next endpoint, we've got to sub in 4. So x equals 4, subbing that in gives us 16 take 8, which is just 8, so 2 root 2. Okay? Now, I want to be a bit more accurate with my sketching, so I'm going to find the actual decimal approximation of 2 root 2. 2.82. 2.82. So that's about, yeah. 4, 2, not the decimal one, but the exact one. There we go. Okay? Now, I actually want to see what the graph kind of looks like, just so my sketch can be accurate, so I'm going to sketch it on the CAS. X squared take 2x, so let's add graphs. We go x squared take 2x. Okay, this is what our graph looks like. We're using that right-hand branch. Okay, so that gives me an idea of how to sketch this. So it's going to look something like that. Okay, sweet. Now it says the portion of the curve that we just drew is rotated around the y-axis to form a solid revolution. Write down a definite integral in terms of t that gives the volume. So we're going to be rotating this around the y-axis to form a nice object. So that's going to involve pi times the integral from our starting y value to our ending y value, so 0 to 2 root 2, of x squared, because we're rotating around the y-axis, so our heights are x's, x squared, and since it's around the y-axis, it's dy, okay? Now the main issue here is that it says in terms of t, so we need to convert everything here in terms of t, all right? Let's start off with the terminals. So our terminals here are y equals 2 root 2 and y equals 0. Going up here, we know what y is in terms of t. Y is equal to tan of t. So this means that 2 root 2 is equal to tan of t, and that means t is equal to tan inverse of 2 root 2, okay? And similarly here, 0 is equal to tan of t. That means t is just equal to 0. So that one doesn't change, okay? So our new integral is going to have terminals from 0 to tan inverse of 2 root 2. Now, x squared, right? We don't want x squared there. We want to replace it with what we have here for x. So that's going to be sec t plus 1 all squared. Okay? Now, we still have our dy. That's not very useful to us, right? We need dt's. So using this, we can actually work out dy on dt is equal to sec squared of t, okay? Multiplying this across gives us dy is equal to sec squared of t dt, okay? And that's really useful for us because we can replace this dy with sec squared t dt. And that's our answer. All right, that was an adventure. All right, question 2. It says show that the solutions of that are that. Okay, so I'm just going to use the quadratic formula. So I'm going to go z is equal to negative b plus or minus root b squared take 4ac, okay, on 2a, so 4. Now our next line is going to be negative 4 plus or minus, what does that become in the square root? We get 16 take 40, which is negative 24. All right, now getting that negative out of that square root gives us an I on the outside. I can rewrite that square root as root 6 times root 4. Root 4 is just 2, so I can write it as 2 root 6. And that simplifies to negative 2 plus or minus root 6i on 2. And splitting this gives us negative 1 plus root 6 on 2i, or negative 1 minus root 6 on 2i. And they are our solutions. Okay. Now it says plot the solutions of that on the Argand diagram below. So looking at this, our real component is negative 1, and our imaginary components are root 6 on 2 and negative root 6 on 2. So I'm going to go on the CAS and see what the decimal approximation of root 6 on 2 is, just so I can actually sketch it a bit more accurately. So let's go root 6 divided by 2. That gives us 1.22. Okay. So we're going to be negative 1 and 1.22 up. So that's going to give us our solution up here, and negative 1 and 1.22 down. So that's going to be about down here. And we've got to label our solutions as well. So that's going to be negative 1 plus root 6 on 2i. And this is going to be negative 1 minus root 6 on 2i. Perfect. Okay. Let the absolute value of z plus m equal n, where m and n are real numbers, represent the circle of minimum radius that passes through the solutions of that. Find m and n. Okay, so on first glance, this might seem a little bit confusing, but going back up here, let's kind of visualize what the circle would look like. It would look like that, right? Something like that. And the middle would be at negative 1, 0. Now, thinking about that, what would our radius be? Wouldn't our radius be our imaginary component? It would just be root 6 on 2, okay? So coming back down here, m is how much you're translating it left and right. So we've translated it 1 to the left, right? So that means m needs to be equal to 1, okay? And n is our radius, so that means n is equal to root 6 on 2. Nice and easy, once you kind of conceptualize and visualize it. Find the Cartesian equation. Now, we know the center of the circle is negative 1, 0, so that means our Cartesian equation is going to be x plus 1 squared plus y squared is equal to our radius squared, which is this. Once we square that, we get 6 on 4, or 3 on 2. Okay, now here it says sketch the circle. We already did that. You don't need to label anything. It doesn't say you need to, so that's perfect. Now part C. Find all values of D for which the solutions of that satisfy the relation of that circle. Okay, so this means our solutions need to be either on that circle or within that circle. That's what it means visually. So I'm going to actually solve for the solutions. So let's go z is equal to negative 4 plus or minus root b squared, which is 16, take 4ac, which is in this case d. So, and then our denominator is 2a, which is 4. And that leaves us with negative 1 plus root 16 take 8d on 4 or -1 minus root 16 take 8d on 4. Now, these are our solutions, right? And looking back at our previous question, right, we had -1, and adding a certain value to it moved it further away from that point. And looking back here, we have a similar thing happening. That means whatever we're adding to it, the absolute value or the magnitude of it needs to be either equal to the radius or smaller than the radius, because if it's bigger than the radius, it's not on the circle, or it's not within that circle anymore, is it? So what we need to say is the absolute value of whatever we're adding to that -1 needs to be equal or less than the radius that we found, okay? So coming back here, the absolute value of whatever we're adding, which is the same or subtracting on both ends, needs to be less than or equal to our radius, okay? Let that sink in a bit, and let's put this on our CAS, all right? So let's solve algebra, absolute value. We're going to get, what was it? 16 minus 8d. 16 minus 8 times x. I'm just going to use x on 4 is less than or equal to our radius, which was root 6 on 2. And we've got to solve for x. That gives us x, or d in our case, being in between -1 and 5. So that leaves us with d is in between -1 and 5. Okay? That's our answer there. Now it says all complex solutions of that equation have non-zero real and imaginary parts. Let that be the circle with the minimum radius in the complex plane that passes through the solution. So it's a similar train of thought again. So I'm going to solve for the solutions once again. And this is just a general form. So our solutions are literally just the quadratic formula. B squared minus 4ac all over 2a. Okay? Now splitting this up gives us -b on 2a plus b squared take 4ac on 2a, or -b on 2a minus the same thing. Okay? Now, an important piece of information from this question is that the solutions have non-zero real and imaginary parts, right? This is real. That means the only way we can get a non-real result is if the thing in our square root is less than 0, okay? That'll be useful in a bit. Now, using the logic that we used before with our circle, let's kind of draw what our circle could look like. Right? Our center is going to be at -b on 2a, right? So that means we need to translate this b on 2a to the left, right? So that means p needs to be positive b on 2a, okay? If it was negative, it'd be moving it to the right. This is why it needs to be positive. Now, this is equal to our radius. Our radius in this case is q, okay? So this means that q is actually the absolute value of what we're adding to -b on 2a, right? As we said before, if you add the radius, you're going to get on that circle, right? So that means q is equal to the absolute value or the magnitude of what we're adding. So it needs to be okay. And going on the CAS, that gives us absolute value of root. You can just do this by hand if you know how magnitudes work. What was it? B squared minus 4ac. B squared minus 4ac. Whoops, why is that up there? Minus 4ac on 2a. Okay, that's what it gives us, right? It gives us that as a result. Okay, that makes sense. So that means, right, taking the absolute value of this whole thing is the same thing as having the absolute value of A over the absolute value of whatever's on the inside. Okay, because remember, we said at the start that it was negative. When we take the absolute value, we need to make sure that this is the real result now, because this is just the magnitude. And we can just get rid of those exact value symbols in the square root by just having a negative in there, because that will make it a positive, right? If we come up here and multiply everything by a negative, that's going to flip this, and now that is positive. So this is a real result, and that's our magnitude. So this is what Q is equal to, okay? These are our two answers. Boy, that was an adventure. Now, question 3. The growth and decay of a quantity P with respect to time is modeled by the differential equation below. Okay, that. Okay, given that P of A is R, P of B is S, where P is a function of T, show that K is that. Okay. So, what I'm going to do first is I'm going to take the reciprocal of this. dt on dP is equal to 1 on Kp. I'm going to do that so I can integrate this now. So now I get T is equal to the integral of this with respect to P. Okay. This yields me 1 on K log E absolute value of P plus CT. Okay. Now let's use these pieces of information that they've given us. It says when you sub in A into T, right? I'm going to do it in a different color just so it's a bit clearer. When you sub in A, you get P being R, okay? And then using the next piece of information, we get, when you sub in B into T, you get P being S, okay? This is our first equation, this is our second equation. Now, we can just subtract these equations, and that will give us A minus B is equal to 1 on K log E R minus 1 on K log E S. And the C's just cancel out because C minus C is 0. Now, on the right-hand side, we can use our log laws to combine the logs by writing it as log E of R on S, okay? The left-hand side stays the same for now. Now, what we can do is take the reciprocal of both sides. We get 1 on A minus B is equal to, flipping the K gives us K on the top, flipping the log gives it on the bottom. And then finally, multiplying by log E R on S for both sides gives us K is equal to 1 on A minus B log base E of R on S. Sweet, and that's what they wanted us to show, right? Nice, that's our answer. Okay, now it says specify the conditions for which K is positive. Okay, K is positive. So, here we have two things that are multiplying by each other. What does each term need to be in order for the product to be positive? Wouldn't you need to have this being positive and this being positive, or this being negative and that being negative at the same time, right? So we've got case 1. We have both of them being positive. So we have to write this is positive, and at the same time, log E R on S is also positive, okay? And that gives us A minus B is greater than 0, and that tells us that A is greater than B, okay? That is our first one, so that's that there. And then we also have and. It needs to be an and because they need to happen simultaneously. This gives us R on S is greater than 1, okay? Which gives us R is greater than S, right? Okay. Yep. Okay, so these two are a pair of solutions. Okay, that will give you 1 mark. Now, case 2 is actually when both of them are negative. So we're going to have to write 1 on a minus b is negative, which implies that a minus b is less than 0, which means that a is less than b. Okay? A is less than b. So that's one of our things there. And then for the next part, we need to have log e r and s being negative as well. And this implies that r on s is less than 1, which means that r is less than s. Okay? So these need to happen at the same time. If you're wondering how I'm getting from here to here, all I'm doing is just taking e of both sides. They cancel. This becomes 1. Okay? Or you can logically think and say that in order for that to be less than 0 and negative, this needs to be a fraction that is less than 1. Okay? So these are our pairs as well. Okay? They need to be in that arrangement. The growth of another quantity q with respect to time is modeled by the differential equation below. Express this differential equation in that form. Okay. So what I'm going to do first is I'm going to write this as dq on dt is equal to, using our index laws, we get e to the t on e to the q. Okay. And then multiplying by that across and that across gives us dq eq is equal to et dt. Okay? And then taking the integral of both sides gives us the integral eq dq is equal to the integral of et dt. Okay? Now it says hence show that q is equal to that. Okay, so let's integrate both sides. We get e to the q plus c is equal to e to the t. We don't need a plus c on that side because even if I had a plus d, for example, when I bring them to one side, they form one constant anyway, so you don't need it on both sides. Okay, so using this piece of information here, we can work out what c is. So we go e to the 1 plus c is equal to e to the 0. Right, all I did was sub them in. That gives me c is equal to 1 minus e. Sweet. So subbing that back in, we get e to the q plus 1 minus e is equal to e to the t. Now it wants us to solve for q, so I'm going to go e to the q is equal to e to the t plus e minus 1. And then finally, log e of e to the t plus e minus 1 is equal to q. Okay, that's what they wanted us to show. Now it says, show that the graph of q as a function of t does not have a point of inflection. Okay? So first what I'm going to do is, I'm going to differentiate this. So I'm going to get dq on dt is equal to derivative of the whole thing, keeping the inside the same, times by the derivative of the inside. Okay? I can bring that up here. And then now we're going to differentiate it again using the quotient rule, or you can use your CAS. We get derivative of the top times the bottom minus derivative of the bottom times the top, which just combines to be e to the 2t. Okay, and this whole thing is on the bottom squared. Now, cleaning up the numerator a little bit, when I expand the bracket, I get e to the 2t plus e to the t plus 1 minus e to the t minus e to the 2t over our denominator squared. Now, these two cancel, and that leaves us with e to the t plus 1 minus e to the t. Okay, for this to not have a point of inflection, this second derivative needs to be always positive, okay? Because this is always positive, right? And that means this is always positive, okay? So that means e to the t plus 1, take e to the t, is always positive, which means that is true, which means that is true, and that means 1 is greater than 0. Obviously, that's true. So that's true. Like, that makes sense, right? That's a valid statement. So you're saying that d squared dt squared is positive, therefore no point of inflection. Because for a point of inflection, your second derivative needs to equal 0 at that point, right? Yeah. Where is t defined for again? T is just greater than or equal to 0. Yeah, okay, that makes sense. Okay, the next question. The base of a pyramid is the parallelogram ABCD with vertices. Okay, I'm going to draw this. Drawing it is always recommended. Makes your life a bit easier. We got A, B, C, and D. Okay. All right. Now, I'll actually just write the vector next to it as well, just so it's a bit easier for us later on. A, B, C, D. B is 4, -2, 1, and A is 2, -1, 3. Okay. Now, I'm going to actually move this a little bit just so it's clearer. When we have a clear diagram, everything will be easier. We also have the point P. Let's move this as well. Point P. And this is a pyramid, so it should have a point up here. Right, sweet. Now remember, these are vectors, so they're all from a particular origin. Now let's draw in the lines that actually denote the vectors. We've got an arrow there, arrow there, arrow there, arrow there, finally, an arrow there. Okay, hopefully that's not too confusing to follow, but let's go through it now. So it says find the values of A, B, and C. Now looking at the diagram we just drew, right, this side is parallel to that side, right? So if the difference between this I component and this I component is 2, that means the difference between that I component and that I component should also be 2. So that means A is equal to 6. Okay? Now, looking at the J component to -1 to 3, it's 4 higher. So similarly, B should be 4 higher. So B should be 2. And then finally, looking at the K components, 3 and -1. -1 is 4 less, so C should be 4 less than 1. So C is equal to -3. Okay, so C has the coordinates, or the vector. C is 6, 2, -3. Okay. Find the cosine of the angle between the vectors AB and AD. Okay. Let's actually find what AB is. Now, looking at our picture, it actually makes our life a little bit easier. AB is this here, okay? It's that line there. And as you can see from this, AB is going to be AO plus OB, okay? AB is equal to AO plus OB. Now, looking at what we've labelled, AO is just a negative of what we've written down, so it's -2i plus j take 3k plus OB. OB is just a normal B vector, that's 4i take 2j plus k. Okay, and this gives us 2i take j take 2k. All right, this will be useful to us later on as well. So let's work out AD as well. Looking at our diagram, AD, where's AD? AD is this line right here, right? And we can figure out that using AO and OD, okay? So we can figure out AD by using AO and OD. That's going to be negative 2i plus j, take 3k, plus OD, which is 4i plus 3j, take k. Okay? And that gives us a nice 2i plus 4j, take 4k. Okay? Now, it wants the cosine between those vectors. So the cosine between those vectors is going to be AB dot AD over the magnitude of AB times the magnitude of AD. Okay? Now, the dot between those two vectors that we just found is going to be 4 minus 4 plus 8. Okay? And the magnitude of each one, the magnitude of AB is square root of 4 plus 1, which is 5, plus another 4, which is 9. So that's just 3. Times the magnitude of AD. Now the magnitude of AD is just going to be square root. 2 squared is 4, plus 4 squared is 16. So that gives you 4 squared is 16, 20, plus another 4 squared, so that gives you 36. So root 36 is just 6. So that gives us 8 on 18, or 4 on 9 as our cosine. So that's our answer. Okay, find the area of the base of the pyramid. Now, the base of our pyramid is a parallelogram. And the area of a parallelogram is just half base times height, right? Half base times height. Now, the thing here is, how do we figure out the height? The thing is, how do we figure out the height? So, looking at this base of the pyramid, right? It's exactly what we have up here, but this is a bit confusing. I'll just label the vectors again. A, B, and D are the corners we're concerned with. A, B, and I'll just label all of them. A, B, and D. Now, we know the magnitude of AB, right? We just figured it out up here. AB was 3. Now, we also figured out the magnitude of AD. AD was 6. Right? So, the area of this is half base, which is 6, times our height. Now, the height is the thing we need to worry about. Height. Now, look here. We form a right-angled triangle. Let me draw that out here. Our hypotenuse is 3, and the height is what we're trying to figure out. Now, we know cos is 4 on 9. Cos is 4 on 9. Cos of this angle is 4 on 9. So, we can draw a triangle again. Right? And we know the ratio of adjacent to hypotenuse. Okay? And that leaves us with one unknown. Okay? And that will let us work out sine. So, how do we figure out this unknown? It's 4 squared plus the unknown squared, I'll call it x, is equal to 9 squared, which is 81. 81 takes 16 is 65. That gives us x is equal to root 65. Okay? The height of that is root 65. So that means sine of theta is equal to opposite on hypotenuse. Right? So now that we know sine of theta, right, obviously sine of theta is opposite on hypotenuse, so we can go sine of theta, or what we just found, is equal to opposite on hypotenuse. multiplying by 3 across gives us root 65 on 3 is equal to our height. So our final answer, we can replace our height. We go half times 6 times root 65 on 3. Okay, these cancel, and we're left with root 65. I believe I've made a mistake somewhere. Where could I have made the mistake? Did I have the correct magnitude of AD? Yeah, I did. That was 6, right? 4 plus that. Yeah, that was right. Half base, yeah. Now our height. What's the thing that's bad here? No, not half base. I'm dumb. Half base is literally a triangle. You guys must be like, what is this guy doing? The area of a parallelogram is base times height. Okay? And we figured out the height to be this, right? Holy shit. Our base is 6. And our height is what we just found it to be. These cancel and leaves us with 2 root 65. Okay? That's the answer. Don't be dumb like me and write down the wrong formula from the start. Otherwise, the rest of your answer is going to be wrong if you don't pick up on that answer, on that mistake. Okay? Show that 6i plus 2j plus 5k is perpendicular to both those vectors, and then find the unit vector that is perpendicular to the base of the pyramid. Okay, so to show that they're perpendicular, we need to do the dot product and show that it equals 1. So, first off, where's AB? AB is what we found up here. So that's useful. 2i, take j, take 2k. 2i, take j, take 2k. Okay, that's just for note. Dot producting these gives us 12 minus 2 minus 10, which is 0. Therefore, perpendicular. Okay, and then now let's go with the other one. We go 6i plus 2j plus 5k, dotting that with AD. AD is 2i plus 4, take 4. 2, 4 minus 4. That gives us 12 plus 8 minus 20, which is 0, therefore perpendicular. Nice. And then it says find a unit vector that is perpendicular to the base of the pyramid. So unit vector, just call it u hat, is just going to be this, because it's perpendicular, divided by its magnitude. The magnitude of that is going to be root 36 plus 4 plus 25. That gives me root 65. So we go 1 on root 65. And then our vector is obviously the perpendicular one that they've just given us. Okay, that's our 3 marks. Now it says find the volume of the pyramid. Now, to figure out the volume of the pyramid, you can just go to your formula sheet. And it tells you here that it's 1/3 times the base area times the height. So it's 1/3 times the base area times the height. Now, we have the base area, that's 2 root 65. So 1/3 times 2 root 65 times our height. Now, the height of the pyramid is the main thing that we need to figure out. Okay? Now, coming here, this would be the height of the pyramid, right? The projection of one of those slant edges downwards, perpendicular to the base. Now, we can pick any of the slant edges to project. I will pick AP, okay? AP. Now, let's figure out what AP is, right? This is A and this is P. Oops. To figure out AP, I'm going to actually clean the rest of them. Actually, no, let's have that. figure out AP, it's just AO plus OP, right? So AP is equal to AO plus OP, right? That gives us AO is negative 2i plus j take 3k, right? I'm just taking the negative of that, plus OP, which is what they've given us right there. So that's going to be plus 4i take 4j plus 9k. And that's going to give us 2i minus 3j plus 6k. Okay? That is our slant edge for AP. Now, I'll draw a better diagram down here. This is what AP is, right? Now, remember, we have our pyramid. We have our base here. Let's actually draw that better. Okay, it's pretty bad. But yeah, like that, yeah? This is P up here. And this is A, right? We're trying to find the projection of that downwards. So, looking at it 2D, this is AP. And we want to find the scalar resolute in the direction of that perpendicular component that we found, right? Because this height is perpendicular to the base. We just found what that is, yeah? So what we want to do is we want to dot AP. We want to go AP dot the unit vector that we just found before. We need a tilde behind it or below it. What this gives us is the scalar resolute of AP in the direction of that unit vector. And that's going to tell us what that length is. So we're going to know the height, okay? So what this gives us is, when we dot these together, gives us 12 minus 6 plus 30, which is 36 on root 65. Equals 36 on root 65. So this is the height of that pyramid, okay? It's important to understand the concept behind this. This is not the vector resolute, this is the scalar resolute in the direction of that unit vector that we found, because it needs to be perpendicular. So now that we have that, all we need to do is sub that back into our equation. So we go volume is equal to 1/3 times 2 root 65 times 36 on root 65. Now, these cancel, and you're left with, what else cancels? This cancels with this, and that becomes a 12. So the only thing you're left with is a 12 and a 2, which leaves you with 24. So that leaves you with 24 units cubed. Okay, that was rough. Next question, we got mechanics here. Okay, so we got, the general paragraph of describing what you already see. After the mass M1 is released, the following forces measured in newtons act on the system. On the diagram above, show and clearly label the forces acting on each of the masses. Okay, so obviously we've got our normal force. We got our weight force 1. Got our weight force 2. And we have our tension in the string. And the tension here is the same thing as the tension here, because it's all connected. Okay, that's all nice, easy 1 mark. If the system remains in equilibrium after the mass M1 is released, show that sine theta is equal to that. Okay, so let's resolve our forces. So when I draw a dotted line here, this is theta, right? The component going against M2 is going to be M1G. Remember, because weight 1 is actually M1G. That's going to be M1 sine of theta. And that's going to be going against weight 2, which is m2g, okay? And that needs to equal 0 because there's no movement happening. And then now adding this to both sides, or adding the m2g to both sides, gives us m1g sine theta is equal to m2g, dividing by m1g to both sides, we get sine of theta is equal to m2g over m1g. Now the g's cancel out and we're left with m2 on m1. Okay? And that gives us what they wanted us to show. Now it says after the mass m1 is released, the mass m2 falls to the floor. For what values of theta will this occur? So if m2 is falling, right, that means m2 needs to be winning over whatever's pulling m1 down, okay? So that means m2g needs to be winning over this, right? That makes sense, right? Because whatever the force pulling m2 down needs to not cancel out with m1, otherwise it's not going to move, is it? So let's move this down here. And let's solve for theta. So let's divide both sides by m1g. The g's cancel and we're left with m2 over m1 is greater than sine of theta. And that leaves us with, taking the sine inverse of both sides, gives us theta is less than sine inverse of m2 over m1, okay? Now it says, find the magnitude of the acceleration in meters per second squared of the system after the mass m1 is released and before the m2 hits the ground. Okay, so here, what we get is, we need to use F equals ma. The forces are going to be m2 pulling it down, so m2g, and the force opposing it is going to be this one, and that's going to be m1g sine theta, right? And that's going to be equal to the mass of the whole system, which is just m1 plus m2 times a, right? And when we divide both sides by m1 plus m2, we get a is equal to m2g minus m1g sine theta over m1 plus m2. Okay, so that's our answer for that component. All right, now this one is crazy. When you see a 5 mark on your exam, definitely take a minute to breathe. Take a minute to make sure that you fully understand what's going on, because it's a big chunk of your exam that you don't want to miss, right? So it says, after the mass m1 is released and moves up the plane, find the maximum distance in meters that the mass m1 will move up the plane if those parameters are true. So we need to conceptually understand what's going on first, right? Let's clear our force diagram first. Don't do that in the real thing. But when we drop m1, it's going to move 2 meters down until it hits the ground, right? When it does that, m1 has moved up 2 meters, right? That's logical. After it's moved up 2 meters, it's going to have a specific velocity. And that velocity is going to let it travel a little bit more until the velocity is overcome by the acceleration and it reaches 0 and it stops moving. Okay? So there's going to be 2 phases. The first one, we need to figure out what the velocity becomes after a displacement of 2 meters. Then after that, we need to figure out how long it can still travel after it's no longer being accelerated upwards, okay? It's going to be accelerating downwards because of gravity. So that's the conceptual understanding that you need to have. Now let's go back here and let's work this out. So phase 1, right? In phase 1, our acceleration is going to follow this, right? Because here it says before m2 hits the floor, and that was phase 1, right? So using that equation that we just figured out, we can work out our acceleration to be, using m1 equals 2m2. Wherever we see m1, we can replace it with 2m2. We get m2g, take 2m2 g sine of theta on m2 plus m2. That gives us, what does that give us? That gives us, okay, wait, my bad. We need to replace sine of theta with a quarter as well. Quarter, okay? So on the denominator, that gives us 3m2. On the numerator, that gives us m2g minus a half m2g, which is just a half m2g, and that gives us m2g on 6m2, which becomes g on 6, okay, as the m2's cancel. You can do all this on the CAS as well, but doing it by hand allows you guys to see a bit of the process a bit more. So we know that after, or in that phase, our acceleration is this, okay? Now, what we need to do now is use our constant acceleration formulas to actually figure out what our velocity is after that 2 meter displacement, okay? So, what we need to do is, we want to figure out V. Use a different color. We want to figure out V, right? We don't know what V is. We know our initial velocity is 0 because it's not moving right at the start. It's obvious. Our acceleration is g on 6, okay? And our displacement is going to be 2 after that point, right? Because it's moved up 2 at the end of that phase 1, okay? That leaves us to use the equation v squared is equal to u squared plus 2as, okay? V squared is equal to 0 plus 2 times g on 6 times 2. That gives us 4g on 6 v squared, and that gives us v is equal to square root of this, which I'm just going to put on the CAS. Square root of this, obviously the positive version because it's moving up the plane. So, whoops, let's go back, make a new one. Square root of 2 on 3, right? And it was times 9.8. Right? Let's go back to exact. Copy, paste, enter. 7 root 30 on 15. Okay, that's just getting rid of the g now, using 9.8. Okay, so that's our velocity after that phase, right? Phase 2 now. Phase 2 is the important one. And we know that in that phase, he traveled 2 meters, right? So let's write that here. Phase 1, completed 2 meters. Now, phase 2 is what we need to consider now. Phase 2. In phase 2, what we have is a little bit different. We have our final velocity is 0, right, because it stops eventually. Our initial velocity is what we just found. Our acceleration is what we need to consider now. Our displacement is unknown, right? We need to figure out how much it travels at the end. Now, our acceleration is going to change because M2 isn't pulling it down anymore, right? So if M2 is not pulling it down anymore, the only thing acting against it is just M1g sine theta. Okay? That's the only thing affecting it at that point. So let's go back here. So our acceleration against that velocity is negative wait a minute. M1g sine theta. M1g sine theta. Right? Wait, let me think this real quick, because that will give us m1 in the equation, and that's not going to let us find what our displacement is going to be, because we're still going to have an m1 in it. So, my bad. What we're going to get is, you can't just directly work out the acceleration like that. That's stupid. F is equal to ma, right? The force that we just worked out was this, right? Stupid me. I just directly went to acceleration. That is m1g sine theta. So our force is m1g sine theta. And that's equal to our mass times our acceleration. That's what we're trying to find, right? Dividing by m1 gives us g sine theta. And obviously our acceleration is in the opposite direction to our velocity, so we chuck a negative in the front. And that's our, negative should have been there from the start. That's our acceleration. So our acceleration, and obviously we know sine of theta, right? Sine of theta is a quarter. So we don't need any thetas in our equation. Quarter. So our acceleration is negative g on 4, okay? And to work this out, we can actually use the same equation that we used before. So we're going to get v squared is 0 is equal to u squared plus 2 times a times s. Now, s is what we're trying to solve for. So for this, I'm definitely going to use the CAS just so I don't make any mistakes. And yeah, hopefully it turns out right. Okay, so let's go actions, not define. Let's go here. What am I doing? All right, we go here. Then we go 0 is equal to bracket root 7 15. Type this in. This is a bit of a tedious process. You'll probably be able to type this faster on an actual calculator. G, let's use negative 9.8 obviously. And then we go on 4 times s, or we can just use x, and we get 4 on 3, okay? So that yields us, oh, that went all the way down. That yields us s is equal to 4 on 3, okay? So that means after that first phase, travels another 4 on 3 meters. So that means in phase 2, it goes 4 on 3. So that means total is going to be 4 on 3 plus 2, which is just going to be 4 on 3 plus 6 on 3, which is 10 on 3 meters. That is our answer. Now, that is an adventure. Like, that is what makes up a 5-marker. That's a lot of work, okay? But it is 5 marks. It's reasonable. Okay, last question, probability. Company produces packets of noodles. It is known from past experience that the mass of a packet of noodles produced by one of the company's machines is normally distributed with a mean of 375 and a standard deviation of 15. To check the operation of the machine after some repairs, the company's quality control employees select 2 independent random samples of 50 packets and calculate the mean mass of the 50 packets for each random sample. Assume the machine is working properly. Find the probability that at least one random sample will have a mean mass between 370 and 375 grams. Okay, so here, this one's actually really interesting because it has a binomial distribution, or like a binomial style in it as well. And I've never really seen a binomial style question in Spec before. So let's have a crack at this. First, what we need to do is actually work out the chance of getting something, or getting in between 375 or 370 and 375. So we're going to have x bar being normally distributed with a mean of 375, and our standard deviation for the mean mass is going to be different than the population, right? So that's going to be 15 on root 50. And usually this notation has variance in here, so you just square it. It doesn't really change your calculation though. It's just a notation. So now to work this out, I'm going to go probability of this being in between 370 and 375. Okay, and to do this, obviously we've got to use the CAS. So switch over to the CAS. We go normal, not in here, normal CDF. The lower bound is going to be 370. The upper bound is going to be 375. The mean is 375 as our thing showed. And then our standard deviation was 15 on, where is it? 15 on root 50, I believe. And that gives us a probability of 0.4907 equals 0.4907 ... Obviously use your full answers or use your full decimal places for that. Now we have two independent random samples, right? So we have x being binomially distributed, right? Or x bar, I don't like x bar. We'll just use different letter, whatever letter. We'll just use y being binomially distributed. We want y to be at least greater than 1. So y is greater than or equal to 1. That is not how notation works. Okay, n is how many we actually have, 2. And our chance of it being in between that is what we just worked out. Okay, there we go. Now we can have that notation. Probability of y being greater than or equal to 1, okay? And going back here, we're going to use binomial CDF for that. Number of trials was 2 because there's 2 actual samples. Our probability of success, wait, I should have copied this first. Copy that, come here, binomial CDF. Number of trials was 2, probability of success is what I just copied, and lower bound is 1 to 2 because we want at least 1. And that gives us our probability of 0.741. And it wants it to 3 decimal places, so 0.741. That's our answer. Okay. Now, assume that the machine is working properly. Find the probability that the means of the 2 random samples differ by less than 2 grams. Okay. So, we want the means of both of them, right? When you subtract them, the difference needs to either be less than 2 or greater than 2, or greater than negative 2, right? For example, if I have like 6 and 7, obviously they differ by less than 2. So when you subtract them, you get 1. That's in between this, right? That makes sense. Yeah, that, like, as long as you understand that logic, it should be all right. So that is what we're trying to find, right? But in order to figure this out, we need to actually work out the mean of this. The mean of this, or the expected value, is just the mean of each one separately, and you subtract them. Now the mean of the first one is 375, right? And the second one is 375, so this is 0. And then to work out the other piece of information that we need is the standard deviation. We can't calculate the standard deviation directly, but we can calculate the variance. The variance of this, okay? And then square root it to get us the standard deviation. And this is going to be equal to the variance of the first one. That -1 gets squared, becomes a +1. Variance of the second one. And yeah, we'll be able to work it out now. So to get this, remember, we found that the variance was actually this, right? Remember we wrote it down there? Because we found that this is the standard deviation. Squaring it gives us the variance. So both of them have the same variance. So that's going to be 15 on root 50 squared plus 15 on root 50. Oops, I ran out of room there. But it's the same thing twice. Let's move it here. 15 on root 50 squared, all square rooted, gives us... Okay, no, I'm not going to square root it yet. Let's actually work out what that is. It's going to be 15 on root 50 squared plus 15 on root 50 squared. Okay, that's 9. Nice, beautiful. So that gives us 9, and then when you square root it to get the standard deviation, we get standard deviation is 3. Okay, so now to work out this, the probability of it being in between that, right, we can use our normal distribution to figure that out with a mean of 0, standard deviation of 3. So that's going to be going here, normal CDF, lower bound is -2, upper bound is 2, mean is 0, and our standard deviation is 3. That gives us 0.495. 0.495. And it wants it to 3 decimal places, so the chance of this happening, probably right at the bottom, 0.495. Okay, nice. To test whether the machine is working properly after repairs and is still producing packets with a mean mass of 375 grams, the two random samples are combined and the mean mass of 100 packets is found to be 372 grams. Assume that the standard deviation of the mass of the packets is still 15 grams. Okay, a two-tailed test at 5% level of significance is to be carried out. So write down a suitable hypothesis. So our null hypothesis is going to be that the mean is still 375, right? Nothing has changed. But our alternative hypothesis is going to be that the mean is not 375, right? Because it says we're trying to see if it's working properly. It doesn't say if it's less than or greater than. It's just if it's not producing with a mean mass of 375, then it's not working properly. Now it says find the p-value, okay? Now remember, this is a two-tailed test, so let's draw a normal curve. And remember, the p-value, let's actually just not label this first, 375. Remember, this is 372. And we want to find the probability of that happening, but we want to test it two-tailed. So whatever the chance of that is, we need to times it by 2, okay? Now, conceptually, the p-value refers to the probability of getting a result that is as extreme as what you just got or even more extreme, okay? So it's just the chance of it being even less than, like even further away from the mean on both ends because it's two-tailed. So let's go to normal CDF. This is going to be normal CDF. It's going to be from 372, negative infinity. Our mean is 375. And our standard deviation hasn't changed, right? It's 15 on root 50. 15 on root 50. I haven't stuffed anything up. Okay, so that's what it says our one-tailed thing would be, but we need to times it by 2 because it's what is that? Paste, answer. That's what it says that is. Have I stuffed anything up here? Yeah, I did. I wrote down the wrong terminal. Wait, did I? Did I stuff anything up? What did I stuff up? Did I read it right? Yeah, 372. Wait, let's write this anyway. Probability of it. No, we don't need to write any working out. What am I messing up here? The mean is 375. It's still 15 grams. Oh, it's 100 packets. It's It's not 50. Okay, I'm stupid. So the new standard deviation would be 15 on root 100. Yeah. I knew that was sus because, like, it's just 5% level of significance. There's no way this is going to be that much higher than it. Like, it's already high enough there. So let's copy this back down. And this is 100. Okay, that makes a bit more sense. And then let's times that by 2 because it's two-tailed. And that gives us 0.045. Okay, so that's good. And it says 3 decimal places, so we can say that it's 0.046. So that's our p-value. Okay? Does the mean mass of the sample of 100 packets suggest that the machine is working properly at the 5% level of significance for a two-tailed test? Okay, so conceptually, the p-value is the chance of getting a result that is as extreme as what you just got, or even more extreme, given that the mean is that, right? So here we have our p-value being less than 0.05, right? And logically, what that means is the chance of this happening is too low for it to happen in reality if the mean is actually 375, right? Let me repeat that. The p-value is the chance of getting a result that's as far as what you just got, or even more extreme, given that the mean is actually 375. The fact that we got something lower than the significance level means that the chance of it happening is way too low in reality for it to happen if the mean was actually 375. That means the mean has to actually be different. Okay, that's the logic. So therefore you say, because of that, you say reject HO, right? Because it can't actually be that mean. And therefore you say the machine is not working properly. Okay, that's the conclusion. Now it says, what is the smallest value of the mean mass of the sample of 100 packets for HO to not be rejected? So let's draw our normal distribution again. We have 375. And we have the smallest value. Let's just call it n, right? And the probability to the left of it needs to be 0.025. And the reason for that is, remember, we multiply it by 2 because it's a two-tailed test. So it needs to be half of this to where you multiply it by 2, it gets you 0.05, and H0 is not rejected, okay? So to work this out, all we need to do is go on to inverse normal, right? And we say our area, right, the left-hand side, I just wrote down 0.025. Our mean is 375, and our standard deviation is 15 on root 100, which is just 10. And that gives us 372.06. To one decimal place, it's just 372.1. That is the smallest value. Oh, that was quite a journey. Hope you all enjoyed that. That was definitely an exam to behold, but yeah, good luck.